AI data centers are starving for power. Traditional chips are hitting a hard physical wall. But what if the ultimate computer already exists inside your head?
Training and operating modern AI models requires a staggering amount of electricity. We are feeding gigawatts of power into these systems every single day just to keep up with the math. That energy demand translates into a massive physical footprint. To run these calculations, companies build warehouse-scale data centers packed with dense rows of server racks that stretch as far as the eye can see. All those servers generate intense heat. Preventing a total meltdown requires a separate, massive infrastructure of industrial cooling pipes and climate control machinery running constantly. Right now, the hardware industry is solving the demand for more AI compute through brute force, stacking chips sideways to push more data through. But silicon can only handle so much heat before it degrades. We are packing these chips so closely together that the thermal output is becoming unmanageable. We are hitting a physical thermodynamic wall. We cannot sustain progress simply by feeding more power to traditional machines. The root of this energy crisis dates back to the very first room-sized computers. The architecture they rely on keeps the processor, which does the math, physically separated from the memory bank, which stores the data. In computing, this design is the von Neumann bottleneck, a narrow bridge connecting logic to stored information. To run a calculation, AI must physically ferry data across this bridge. Moving that information burns significantly more energy than the actual calculation itself. A split architecture designed in the 1940s is physically incompatible with the massive, continuous data flow required by modern AI systems. Compare those gigawatt data centers to the human brain. It manages operations far more complex than our most advanced models, yet it runs on roughly 20 watts, about the same power as a common LED bulb. Biological neurons do not separate logic from storage. They handle processing and memory simultaneously, acting as both in the exact same physical space. By co-locating compute and memory into a single node, the energy-draining data commute is eradicated at the source. Traditional computer chips also waste immense power through a relentless, constant clock cycle. They tick billions of times a second. That constant ticking draws a heavy load of electricity, even when the chip is idle, waiting for new information to arrive. To fix this, researchers are developing spiking neural networks. Modeled after biology, these interconnected nodes sit completely dark and inactive most of the time. They are event-based. The network remains dormant, drawing almost zero power, until a specific stimulus enters the system. Only then do the pathways flash with rapid electrical spikes. Hardware manufacturers are now turning this concept into physical silicon. Intel's Loihi research chip and IBM's Hermes cores use this single spike computation to process information only when an event requires it. Combining in-memory compute with event-based spiking creates an architecture that slashes AI power consumption to a fraction of conventional limits. When an AI processor requires only milliwatts of power to function, it no longer needs to be tethered to a giant, power-hungry server farm. This enables edge computing. We can run complex AI algorithms locally, directly on the device, without a constant connection to a data center. In practice, a prosthetic leg equipped with an edge processor can detect an unexpected trip and instantly adjust its mechanical joints, without waiting for data to travel to a server and back. Autonomous robots can visually react to fast-moving objects in real time, and specialized chips can even be programmed to identify hazardous chemicals by their molecular signature. Neuromorphic hardware empowers AI to leave the sterile environment of the data center and operate dynamically in the unpredictable physical world. The age of solving every computational hurdle by simply feeding more electricity into a hotter chip is reaching its limit. The next stage of development isn't about more power. It's about a structural change in how we process information, prioritizing biological elegance over mechanical force. To build a truly artificial brain, engineers finally had to start building computers that actually look and function like biology.
Welcome to this explainer. Right now, the AI revolution we are all kind of living through is on a high-speed collision course with the fundamental laws of physics. We are simply running out of power, and we're running out of space. So today, we're going to explore how the next generation of computing is bypassing traditional silicon structures entirely and taking a blueprint straight from human biology to overcome these physical limits. Let's dive into it. Imagine for a second, what if a computer chip could literally sniff out a hazardous chemical? Or what if it could grant a lab robot a genuine physical sense of touch? I know, it sounds like pure science fiction, but this isn't some concept that's decades away. It is happening right now in research labs across the world. But to really understand how these incredible sensory feats are even possible, we first have to talk about the massive wall that traditional AI is currently crashing into. Section 1. The problem with current AI. See, we're asking our current systems to do way more than they were ever physically designed to handle. When we train large AI models today, we're basically using sheer brute force. Traditional AI hardware requires massive server farms, enormous industrial cooling systems, and literally megawatts of power just to function. And a lot of this comes down to what computer scientists call the von Neumann bottleneck. That's the physical gap between a computer's processor and its memory. Constantly shuttling data back and forth across that gap just wastes huge amounts of time and energy. Now, contrast that brute force with the human brain. Your brain processes complex sensory inputs, learns new tasks dynamically, and solves intricate problems. And it does all of that while running on about 20 watts of power. That's roughly what it takes to power a dim light bulb. The tech industry has realized that to keep scaling AI, we can't just keep building bigger server farms. We need to borrow the brain's ultimate low power efficiency. Section 2. Enter neuromorphic computing. And that leads us directly to the biological solution to our silicon problem. Neuromorphic computing is a complete rethinking of computer architecture from the bottom up, designed to function less like traditional computers and a whole lot more like the human brain. We are quite literally throwing out 60 years of foundational computing theory to start entirely from scratch. The crucial takeaway here is that we aren't just trying to cram more microscopic transistors onto a slightly faster chip. We are radically overhauling the hardware to physically replicate how biological neurons learn, organize, and communicate with each other. The academic world is completely on board with this monumental shift, and they kind of have to be. Moore's law is slowing down, and traditional silicon is hitting its physical atomic limits. If you spend any time browsing the computer science archives on Archive, specifically their emerging technologies category, you'll see aggressive tracking of alternatives to standard silicon CMOS tech. Because we just can't shrink standard transistors much further without running into quantum interference, researchers are pouring everything into nanoscale electronics, photonic computing, and quantum technologies to break through these bottlenecks. We're rapidly leaving the traditional silicon era behind. Section 3. Mimicking the human brain. But how do you actually build a brain out of metal and wires? Well, it comes down to mimicking biological functions right there on the physical hardware level. In traditional computing, data processing is highly linear. Like we talked about earlier, you've got a CPU for processing, a separated memory block, and data constantly traveling back and forth. That whole process is drained by a continuous, power-hungry internal clock that just keeps ticking whether it needs to or not. Neuromorphic architecture completely collapses that divide. It integrates memory and processing together, exactly like the biological neurons and synapses inside your head. And instead of that continuous draining clock, this architecture relies on what researchers call spiking neural networks. These are event-driven. They only wake up and fire, or spike, when there's actually relevant information to transmit. If there's no new data, they just sit idle and consume virtually zero power. IEEE Spectrum put it perfectly when they were covering some recent lab breakthroughs. They wrote, "The result is a simple and efficient neuromorphic device that mimics a brain cell. But it is absolutely vital to understand that these aren't just lines of code simulating a brain on a computer screen. We're talking about actual physical materials. Engineers are using components like memristors, which are resistors that literally remember the electrical state they were in. They change their physical resistance based on the electrical spikes they've experienced, adapting just like biological memory. We are literally engineering artificial brain cells right onto silicon chips." Section 4. Heavyweights. Intel and IBM. Taking this from a cool theoretical concept to actual hardware takes massive resources. Which brings us to the tech titans, turning these biological theories into tangible reality. Starting with Intel Labs, the speed of this evolution has been nothing short of breathtaking. Under the guidance of leaders like Mike Davies and Rich Ullig, Intel rapidly iterated from their initial single Loihi research chip. In just a short time, they scaled up to Pohiki Beach, which was a system linking 64 chips together. Then, by March 2020, they pushed the boundary again with Pohiki Springs, integrating 768 Loihi chips. Going from a single chip to a 768-chip massive system in just a few years shows an unbelievable level of validation and corporate investment. And now, they're already advancing further with their second-generation architecture, Loihi 2. Now, I want you to consider this number, 100 million. That is the staggering number of artificial neurons Intel successfully scaled their Loihi spring system to. And here is the absolute kicker. That entire 100 million neuron system fits comfortably inside a chassis the size of just 5 standard servers. To really put that into perspective, replicating that exact amount of neural complexity with traditional brute force AI parameters would require a massive, power-hungry data center footprint, taking up entire rooms and demanding heavy-duty cooling. Here, it takes up the space of a small closet. But Intel is definitely not alone in this race. IBM Research's Zurich lab is pushing a really diverse set of applications for their neuro-inspired AI toolkit. They're developing biologically inspired recurrent neural networks for highly efficient speech-to-text. And amazingly, they're even using deep learning dynamics to predict the intricate musical chords of Johann Sebastian Bach. This specific project proves something huge. Neuromorphic chips aren't just good at sterile math. They handle temporal, flowing, and highly creative data beautifully. On top of that, IBM is accelerating these spiking networks using advanced hardware like memoristic crossbar arrays and the Hermes in-memory compute core, proving that this tech really excels at dynamic real-world tasks. Section 5. Chips that smell and feel. This brings us to, honestly, my favorite part of this explainer, the real-world physical applications of this technology. Looking at the research coming out of Intel's Neuromorphic community, it almost reads like a sci-fi novel. Researchers have actually trained the Loihi chip to sniff out hazardous chemicals. By converting airborne chemical signatures that hit a sensor into electrical spikes, the chip processes those specific chemical patterns exactly the same way an animal's olfactory bulb differentiates odors. It's quite literally an electronic nose. Over in Singapore, researchers are using this exact same event-driven computing to give physical robots a genuine sense of touch, allowing them to instantly feel their surroundings. And they're collaborating with Accenture to process real-time environmental data seamlessly to assist wheelchair-bound pediatric patients. What is truly mind-blowing about this technology is how portable it's becoming. Because these chips run on mere milliwatts of power, they don't need to be tethered to massive power supplies. Researchers at Caltech's Ambra Lab are using a device called Kapoho Bay. It is a simple USB form factor interface for the Loihi chip, and they're using it to control an AMP Pro 3 prosthetic leg. Because the neuromorphic chip processes data just like a biological reflex, it allows the robotic leg to rapidly adapt to unforeseen kinematic disturbances while walking. It's essentially giving the prosthetic its own localized biological reflexes in real time, and it's all running off a device roughly the size of a standard USB memory stick. Section 6. The future of AI hardware. So what does this whole convergence of neuroscience and hardware actually mean for our future? This quote from Intel perfectly sums up the core takeaway. They state, Intel sees its Loihi research chip and future neuromorphic processors defining a new model of programmable computing to serve the world's rising demand for pervasive, intelligent devices. The key word there is pervasive. We simply cannot sustain the energy and size requirements of traditional AI for much longer. Mimicking the extreme efficiency of the human brain is the only viable path forward to a future where your clothes, your walls, and your household appliances could all possess advanced AI-level processing locally. They won't need to ping some massive distant data center because these brain-inspired chips run perfectly on just a few milliwatts of power. We are engineering chips that fire like biological synapses. We're creating hardware that can smell, feel, and dynamically react to physical disturbances just like a living organism. So it really begs the question, if we build computers from the bottom up to act exactly like human brains, what happens when they cross the threshold and actually start thinking like them? It is a fascinating and maybe slightly daunting frontier. Thanks for joining me on this explainer. Keep your curiosity sharp, and I'll see you next time.
Hey everyone, and welcome to The Explainer. I am so incredibly excited to be with you today because we are going to be demystifying a truly fascinating topic. We're looking at how the actual biological brain is actively inspiring the future of computer hardware. You know, the way we build and use computers is on the verge of a literal biological revolution, and today we're zooming in specifically on how Intel's Loihi neuromorphic chips actually work.
All right, here's our roadmap for today. First, rethinking architecture. Second, mimicking the human brain. Third, inside the Loihi chip. Fourth, scaling up to millions. And finally, real-world neuromorphic applications. Let's just dive right in.
Okay, part 1. Rethinking computer architecture.
So, we have this massive elephant in the room when it comes to modern computing right now. As sources from both IBM and IEEE Spectrum point out, AI models are continuously growing at an explosive rate. They are demanding highly advanced features of cognition, and frankly, it's pushing the absolute boundaries of our current compute capabilities, our flexibility, and our energy efficiency. The hardware running today's AI is just incredibly power-hungry. It's a total energy hog. And because sustainability is rapidly becoming a top priority across the tech world, we really can't just keep doing what we've been doing. We desperately need a complete rethinking of computer architecture to create a more energy-efficient paradigm.
Well, that is where neuromorphic computing comes in. Intel defines it as a complete rethinking of computer architecture from the bottom up. The ultimate goal here is to take the very latest insights from neuroscience and actually apply them to create chips that function a lot less like your standard laptop and a lot more like the human brain. And it's crucial to understand, this isn't just a clever software update. It is a fundamental, bottom-up hardware revolution.
Section 2. Mimicking the human brain.
You see, neuromorphic systems don't just loosely borrow a few neat concepts from biology, they literally replicate its physical structure. First, they replicate how neurons are organized. Second, they mimic exactly how those neurons communicate with one another. And third, and to me this is absolutely the most impressive part, they replicate how neurons learn at the actual hardware level. So instead of a traditional processor that's constantly running back and forth to fetch data from a separate memory bank, the processing and the memory are deeply intertwined. It's like a giant puzzle where everything is connected, just like the synapses in your head.
IBM research really hit the nail on the head here. They noted that the ultimate goal of this neuro-inspired AI is to optimize the learning and computing efficiency of next-generation AI. By leveraging this brilliant inspiration from biology and combining it with advanced machine learning, researchers are directly tackling those massive energy and efficiency bottlenecks that could otherwise completely stall the future of artificial intelligence.
Section 3. Inside the Loihi chip.
So, say hello to Loihi. Intel's Loihi research chip basically defines an entirely new model of programmable computing. This is the foundational building block for a whole new era. We're moving really fast toward a world of pervasive, intelligent devices everywhere, and Loihi is the exact kind of architecture we need to serve that rising global demand, without just burning through unsustainable amounts of power.
But you might be wondering, how does it actually work under the hood? Well, Loihi processes information using what are called spiking neural networks. What you really need to take away from that fancy term is that it allows the hardware to learn and adapt exactly like your own human synapses do. Why does this matter? Because this hardware is essentially self-learning on the fly. It is dynamically adapting to new information at the hardware level, exactly like a biological brain cell adapting to new stimuli. It's wild.
All right, Section 4, scaling up to millions. Let's see how this actually builds up physically, because the way Intel groups these chips is super fascinating. Step 1 is just the individual Loihi neuromorphic chip. But then in Step 2, Intel places between 8 to 32 of these chips onto what they call a Nahuku board. Okay, then Step 3, they combine multiple Nahuku boards together to create a much bigger system called Pahokee Beach, which contains 64 Loihi chips. And finally, Step 4 takes us to Pahokee Springs, which is this massive system integrating a staggering 768 Loihi chips all working together.
And when you scale all the way up to Pahokee Springs with those 768 chips, you reach this absolutely incredible number, 100 million. That is the total scale of computing neurons achieved by the Pahokee Springs research system. We are literally talking about 100 million artificial neurons wired together to process information. To put that 100 million neuron scale into perspective, it perfectly illustrates the space and energy efficiency of neuromorphic systems. If you look at standard data centers today, you see endless aisles of massive, humming, energy-draining server racks, right? But Pahokee Springs, despite packing in 100 million neurons across 768 chips, fits inside a chassis the size of just 5 standard servers. It's a rack-mounted system that somehow concentrates an unbelievable amount of brain-inspired computing power into a highly efficient, incredibly compact physical footprint.
But hey, scaling isn't always about going massive and building huge data centers. Sometimes it's about going incredibly small and accessible. Enter Kapoho Bay. This is a USB form factor that actually brings the Loihi neuromorphic chip directly to peripheral edge devices. By putting this ridiculously complex technology onto a simple USB interface, researchers can practically plug a self-learning brain right into edge devices out in the field. How cool is that?
Section 5. Real-world neuromorphic applications. The sheer variety of real-world tests happening with this tech right now is just mind-blowing to me. First off, researchers are literally using Intel's neuromorphic chips to sniff out hazardous chemicals. Yes, they are creating computers that can smell. Second, over at Caltech's Ambr Lab, they're using that Kapoho Bay USB device we just talked about to control the Ampro 3 prosthetic leg, allowing the leg to organically adapt on the fly to unforeseen walking disturbances. And third, researchers actually used Loihi to automate a foosball table using visual input from event-based cameras. I mean, foosball requires rapid, closed-loop sensing and planning, which makes it the absolute perfect test for a chip that processes information like a human. And speaking of visual inputs, I love this little anecdote from the Intel labs. The head of Intel's neuromorphic computing program, Mike Davies, used a bobblehead of the famous scientist Rosalind Franklin to test the chip out. Loihi, operating purely as a self-learning research chip, was able to quickly learn and visually identify the bobblehead all on its own. It perfectly demonstrates the rapid, closed-loop sensing and learning capabilities of this chip. It's not just passively crunching data, it is recognizing and dynamically adapting to visual stimuli in real time. And that leads us right into this amazing headline from the Intel newsroom. Singapore researchers are actively looking to Intel neuromorphic computing to help enable robots that feel. Because this architecture mimics biology so incredibly well, it points to a very near future where machines can process sensory inputs from artificial skin, much in the same way human nerves and brains process the sensation of touch.
Which leaves us with this one final provocative thought. If a silicon chip can already be programmed to smell hazardous chemicals, visually identify objects on the fly, and physically feel movement to adjust a walking stride, what exactly will neuro-inspired AI learn to do next? As we move away from traditional energy-hungry computers and toward highly efficient brain-like architecture, the possibilities are genuinely limitless. Thank you so much for joining me for this explainer, and definitely keep your eyes on the fascinating world of neuromorphic computing.
Every day, laboratories across the world push out a staggering volume of computer science research. From leaps in artificial intelligence to novel semiconductor architectures, the sheer velocity of modern discovery generates thousands of new papers every single month. To see how hard this is to organize, look at a breakthrough like neuromorphic computing. This is a radical approach to hardware design that physically mimics the architecture of the biological human brain. These concepts are already etched into silicon. Devices like Intel's Loihi research chip and IBM's neuro-inspired cores exist right now as physical hardware. Once a lab achieves a milestone like this, the researchers face an immediate practical problem. They have to publish their findings in a way that allows other scientists to actually find the work in a sea of daily uploads. Precise categorization provides the roadmap for the rest of the community. It allows other researchers to pull up the schematics, replicate the results, and build upon the original work. That global community lives on arXiv, the massive preprint server where the majority of new computer science papers are uploaded and shared. Since January of 1993, the overarching CS archive has acted as a granular taxonomy, mapping the digital frontier paper by paper. So let's put it to the test. If we write a paper on our neuromorphic chip, where does it belong? We immediately run into a complication. The chip is a multidisciplinary anomaly, part hardware, part artificial intelligence, and part biology. It defies a single label. A filing system has to somehow capture fluid, boundary-breaking innovation. If the taxonomy is too rigid, these new discoveries risk being missed by the very people who need to see them. Every category on arXiv relies on a simple prefix system. You start with the CS umbrella, followed by a specific two-letter identifier. Since our chip mimics a brain to process information, the most obvious choice is CS.AI for artificial intelligence. But arXiv categories have clear borders. The AI category explicitly states that it covers all areas of AI except vision, robotics, and machine learning. That section is specifically for concepts like expert systems, theorem proving, and abstract knowledge representation. Our physical, biologically inspired chip doesn't fit the criteria. If your work touches on pattern recognition or algorithm training, you have to route it to the specific machine learning category, CS.LG, or computer vision, CS.CV. Defining a category by what it explicitly excludes is a deliberate design choice. It prevents high-level categories from becoming overcrowded with papers that belong in more specialized domains. Let's pivot and look at the physical nature of the neuromorphic chip. That leads us to CS.AR, the hardware architecture category. Read the description for AR, and you'll find references to specific ACM subject classes like C0, C1, and C5. These codes come from the Association for Computing Machinery. Archive uses this standardized framework to give its modern categories a grounded, objective foundation. Because our neuromorphic device relies on specific systems organization and physical circuitry, those C-class codes explicitly cover physical hardware, validating the AR match. Tethering new technology to historical foundational definitions provides a common language for researchers. Without these shared coordinates, a specific paper faces a much harder path to being cited or built upon by others. We have a match, but AR only captures physical hardware. It ignores the biological inspiration driving the chip's design. To cover that, we look to CS.NE. Neural and evolutionary computing is the designated home for connectionism, artificial life, and adaptive behavior. And because this chip relies on an alternative to standard silicon CMOS technology, we also fit into CS.ET, emerging technologies. The platform handles this overlap through cross-listing. Instead of being restricted to one box, researchers declare one primary category and supplement it with secondary CAGs, placing the paper at the intersection of several fields. Combining architecture, neural computing, and emerging technologies creates a highly precise digital footprint for the research. This granular intersection allows the database to accurately map multidisciplinary science without forcing researchers to compromise the specific identity of their work. The archive taxonomy evolves alongside the technology it tracks. This chart tracks the volume of submissions over the last decade. Categories like machine learning and computer vision have seen exponential growth, dramatically shifting the weight of the entire database. And future technologies are already testing the system. Engineers are developing optical tech that updates AI on the fly using light, and advanced spiky neural networks that will continue to blur established disciplinary lines. The system accommodates these blurred lines by allowing scientists to draw new, precise intersections across the research network. By providing structured coordinates for every breakthrough, Archive ensures these insights remain visible. It turns a massive, disparate collection of data into an organized foundation researchers can use to push boundaries further.
Nature solved the energy crisis millions of years ago, and now we're finally copying its homework. Brain-inspired computing is rewriting the rules of AI. If you want to stay ahead of the next frontier in tech, hit subscribe and check out our deep dive on room temperature quantum computing right here.